Good afternoon, everybody, and welcome to this critical insight panel entitled Air Cooling versus Liquid Cooling. My name is John Booth, and I'm the MD and Principal Consultant of Carbon 3 IT Limited, the Sustainable ICT Consultancy. I'd like to welcome my guests, Matt Evans, Global Director of Data Center Solutions, Flakt Group, and Andy Young, the Chief Technical Officer of Asperitas. My video is off. That's probably a good thing. Right, so gentlemen, I think it's fairly safe to say that we stand on the cusp of a fundamental change in the way that we do cooling in data centers. Traditionally, it's all been air, but over the last 10 years or so, we've seen the development of liquid cooling in various forms. And due to the projected growth of AI, some commentators have forecast greater use of liquid as the primary cooling method for hyperscalers and others. What are your thoughts on this fundamental shift, Matt?
Thanks for the introduction, John. I guess there is there, and there will continue to be a trend. Densities at chip level, and I kind of highlight chip level, not rack level. We're not really at that sort of stack it high level anymore. They're going up and up. Will it continue, or will there need to be a shift in terms of electronics design? The actual heat rejection design, both. I think there's an element of that going on, but the primary question: will liquid cooling be the primary cooling method for hyperscalers? No, there isn't a requirement that every data center, in fact, very few, are racked to the brim with huge AI, HPC, very high compute racks. There'll be some, there'll be none, and there'll be a hybrid. And what that hybrid looks like will, as always, depend on the workload, the locale, the customer actual requirement. And, I think we've all been saying this, and Andy as well, and Asperitas, it's about picking the best solution for the job, just as it's always been. And, the browbeating that seems to exist in this industry when something new arrives, one size doesn't fit all.
That's a great comment. Andy, what's your view?
Yeah, thanks again for the introduction. Indeed, one size doesn't fit all. As you get older, you need to wear elasticated trousers, and I think there's some flexibility required in the industry to consider all options, really, because certainly nobody can stand here and say they see the future. Nobody can say that definitively this is the solution, and if anybody attempts to do that, then it's a very fun game for the other people around them to play. So really, liquid cooling is part of the mix. It is now, and it will continue to be in the future. I think everyone knows the benefits of liquid versus air in terms of the fundamental ability to shift heat around, but actually the whole value proposition for making a certain choice on cooling technologies really comes down to a business decision first. And whilst we're talking about chip densities, amounts of heat, temperatures, it's really the business case and the value proposition that needs to be considered first. However, having said that, there are some challenges ahead. We can see chassis of servers increasing in the U height. It does mean that handling those chassis becomes harder and harder as the volumetric airflows have to increase. The weight of them is obviously going to increase, and the material costs, the fan power to displace the air to cool is obviously something which aggressively increases with the flow rates. I think it's a cubic relationship. So if you can afford the power and if you can afford the space, and yes, maybe hyperscalers, they have more options there, but power availability, the business case when you're adopting technology, all these business levers have to be considered when you're looking at all the options. And there's increasing environmental regulation and pressure from governmental guidelines and codes of conduct, which are really indicating a direction of travel in the industry.
Very good. And you touched on the point there, availability of power. And I've been to a couple of conferences over the last couple of weeks, and I've heard some absolutely, truly alarming power numbers from the use of the new chipsets for AI. So my next question really is availability of power. Is there enough power available in the locations where the AI is projected to go? And more importantly, I think, can the liquid solution scale to that requirement.
I just wanted to pick on a few things that Andy said then. We're talking about power usage of liquid versus air. All right, we're talking here, Andy works for a single phase immersion cooling company, but there isn't really that much difference between it. I mean, if we start looking seriously at this, and I'm sure we'll get into sort of chip level temperature requirements and that sort of stuff, but the real world is very different to the paper-based world. We're looking at primary flow temperature requirements for high-performance workloads that immersion can't really keep up with. And even on direct-to-chip, they're going down into the low sort of teens. This sort of thing about there being huge high-temperature water, lower power usage, all that stuff. If you were to look at a real-world sort of example, you've got heat island effects on top of roofs, you've got global warming, most locales are running at 40 plus ambient, part load figures, which is where most of this is running. A very well designed air cooled system isn't that much more power inefficient than liquid. But, again, on environmental as well, you've got baths full of liquid plastic, probably all derivatives, having to clean all the servers down with solvents to get them into a maintainable state. I don't really subscribe to the environmental side of it, particularly with single phase, direct to chip, rear door, maybe. But the scalability part of it, power in terms of availability, that's nothing to do with my business, unfortunately. Here it's that's something at a local legislative government level and all the rest of it, power companies. Scalability from an actual deployment perspective. I look at the parallel with rear door heat exchangers. I've installed, commissioned, designed a lot of facilities with those. It's very similar to chilled water fan walls, chilled water crack units. Compared with something like immersion, which is it's a completely different design, floor loadings, floor space, all that sort of stuff. So there is a very big divide, I think, with the liquid cooling from a scalability perspective. I did see an absolutely fantastic solution yesterday from HPE Cray, which was a full board level direct to chip, so you needed absolutely no air cooling at all. So that solved a hell of a lot of problems in one go. So yeah, again, I don't see the scalability as a problem. It's a different problem. I think the different forms of liquid cooling immersion, I think, is a bit behind the curve for hyperscale. I think it's an absolutely fantastic solution for, maybe enterprise, industrial factory level. But yeah, that's my take on it.
Yeah. I think, certainly if you pick a context such as hyperscale, then you're going to see things differently to what you would for edge, for enterprise cloud. So context is key here. And, we're making generalizations, but of course, behind that, there has to be a certain context. But I think, fundamentally, if you don't need a fan, or if you remove a heat exchanger from a loop, you're going to have a higher performance. It's fundamental that if your overhead power is reduced, or if you can consolidate the displacement of your coolant within a pipe rather than a room or a duct, if you can remove a heat exchanger step by not using, necessarily technology cooling systems and using facility water directly, then that's going to have an effect on your capital equipment and your operational losses. But of course, that's a generalization. You have to look at the specifics of a site, and it's only when you make good comparisons can you really see the truth behind this. In terms of the availability of power, I think the point I would like to make here is that whatever power you have available, you want as much of that to be available to the workload. So wherever you can remove overheads, and this is just good practice, right? So removing overheads in the power chain, the critical power path, or removing the overhead power for cooling, no matter what that might be, is going to mean that more of your power is going to be available for workload. And simply in immersion cooling, for example, not having to run fans, that's going to save you 6% or more power, but that's scalable savings, and that can make $1 million savings at scale. So while it may, and that's a marginal gain scenario. So I think there are examples where the sorts of efficiencies that you get from liquid cooling can make a scalable difference.
Just to chuck on that one though, if you're talking about removing steps. We're talking about a chilled water system, say to a fan wall or a crack. Water comes through the chiller or dry cooler, whatever you want to call it, goes through a round tube, plate fin coil. Air gets blown over it, good job done. With an emergency system, you've more than likely got a CDU in the middle of it, which has a heat exchanger and an additional pump, and then you've got an additional heat exchanger within the immersion tank itself. So you've actually added 3 steps compared to that airbase.
Right.
It's a little bit up and down.
Depends where you integrate. It depends where you integrate it. And of course, you can make up scenarios that are going to look good, and you can make up scenarios that are going to look not so good. But there is, I don't think we're here to argue about the benefits of liquid as a material to move energy versus air. And I think as long as you make good choices and do good engineering, then there are benefits to be had.
That's a very good point. Thank you for that. So jury's still out really on the best way, although liquid does seem to have a bit of a advantage in terms of density and the ability to remove heat, so 6 times more than air, I believe. The European Commission and specifically the Energy Efficiency Directive requires data centers of over 1 megawatt to begin to utilize their waste heat, or to provide a technical financial reason not to. I just get this impression that there's a lot of operators in Europe at the moment are desperately trying to find technical and financial reasons not to actually do that. I could be wrong, but that's just my general impression. So obviously, and this question's for you, Matt, is it easy enough to collect the heat that your solutions are collecting and then dissipating out into the atmosphere for waste heat recovery as required by the legislation?
I'm gonna bow down to Andy and not even try and claim any sort of advantages versus liquid on this one. But it's, for me, that is genuinely an easy one. It is possible, especially if we go back to that sort of chip level thermal argument. This panacea of high temperature water giving significantly higher grade heat than being used for air-based systems. There are opportunities. If you were to look at a standard data center and you did it like that, you probably could get fairly high water temperatures. But generally speaking, we're still seeing in the mid 20s, mid to low 30s. Say when we look at an air-based system, so we're using indirect free cooling or indirect water, we're seeing sort of 22, 34 flow return. And that's Celsius. So when you look at that, that is credible to be taken off and used somewhere, boosted by a heat pump, all that sort of stuff. There are other applications as well where indirectly the sort of return air can be used. So a particular project that Flakt has been involved in and been very successful with actually was in Norway, where we put heat recovery cores in the return airstreams. And during winter, when it's snowing and icy, which is a lot of the time in parts of Norway, we were actually defrosting all the car parks, pavements, and all that stuff. So whilst it doesn't sound like a huge thing, that's actually a requirement because it's health and safety. It keeps it does lots of things, but there is opportunity. I think one of the biggest problems we have, and you alluded to it, John, is the infrastructure doesn't exist. There isn't a huge shift. And we need one if we're going to do this properly. Planning, engineering, feasibility, actual real world applications. It's all well and good having, a data center that's working on some gaming load that's providing you waste heat, but it only works at sort of 2 a.m. when everybody's playing Call of Duty. How do you store that heat? How do you use it really? It's all complex, and we're all engineers and we can sort it out, but there's a lot of money involved to do that. And there's a lot of physical money in moving earth, putting pipes in, all that sort of stuff. So it's definitely possible. I think it's a fantastic opportunity. It is possible with air. It's going to be easy with liquid, that's for sure.
Andy, your view on that?
Yeah, I can only agree. It's I think the point I would add is that it's got to start with demand. Any heat recovery project, any heat reuse project, should be driven by the demand for that waste heat. Because if you didn't have a demand, you just you have a pipe stub and nothing to do with it. The demand needs to align in terms of, as was mentioned, there's a big compatibility of the temperature differences. There will be an overhead power requirement to upgrade the heat quality or temperature to make those mismatches. And there's also a need for storage for the temporal mismatch, the supply and demand point that was made. So I think, it's certainly possible. In some locations where you want to place a new data center, there may be demand for district heating, social housing, that kind of thing. Microsites is possible. I've heard of some great examples, actually, of people farming lobster using waste heat, which I think is wonderful. I'd like that in my lab. I'm not sure how.
We actually spoke about that at the Open conference back in February about frisky lobsters, and because apparently 20 to 22 is the optimum breeding cycle for lobsters and other fishies. Are you all right, Andy? Seem to have disappeared.
Have we got another technical issue? You've got the background screen, but no Andy.
Yeah, no Andy.
Should we push on and
yes,
he recovers?
Yes. There is a question that's come up from somebody. I'll answer it when Andy comes back. I agree with what Andy was saying, and I also agree with what you were saying, Matt. And I think the biggest problem to address with the using the waste heat is actually that we need master planning at either country or local level to actually start to put in a requirement for district heating systems to be installed, and the infrastructure at a master planning level. There's a place near me that's just part of the HS2 interchange station, and they have got a requirement to put in ducting for the heat network, but that's kind of separate from the kind of view of the data center operator, I think. And I think there's been a lot of problems with, for instance, in the Netherlands, there is a requirement for, well, not a requirement, but there is a statement made by the Dutch Data Center Association and all of the data centers in the Netherlands that they will give their heat away for free. And that's all very well good, but the user then has to come and put all the infrastructure in to collect it. And I think that's quite an interesting point. This is going to be a very one-sided debate if Andy does. Oh, he's back.
He's back.
Excellent, good stuff. So I was just saying, Andy, that it's all very well having the requirement in legislation to have to use the waste heat, but there really needs to be some planning at government level or even local authority level to actually make use of that heat. I am now going to go back to an article I read last week that there are apparently 11,500 heat networks in the UK. And I'm completely staggered by that number. There was a government report. When you go into it and dig it into a little bit deeper, though, they're not heat networks. There are very few proper district heating networks, but there are a number of kind of shared systems where heat networks are shared with a building adjacent. And let's not forget that actually that was how the Stockholm and a lot of the Nordic data set, district heating systems actually became created. Anyway, my next question is, what's the value proposition in terms of cost and floor space? Do those choices of either going with air or liquid actually stack up in the marketplace? And let's have a brief responses to that one, please.
Yeah.
Shall I go first this time, Matt?
Yeah, go for it, Andy.
Yeah, sure. Okay, so for greenfield, it's very clear. The OPEX, there's clearly a saving with liquid cooling due to the reduction in energy overhead. That's easily demonstrated. For brownfield, it's a bit more complex because it depends on the degrees of change and the utilization rates of the infrastructure while you're making the transition from or gradually introducing liquid alongside air. So there is a situation in brownfield where it could get worse before it gets better, depending on, of course, the situation on a particular site. So brownfield's a bit more of a complex image, but one of the case studies for this would be when you've got stranded power that you can unlock by placing liquid cooling, which is a far easier thing to do than it is if you don't have the space availability, for example. So there are definitely savings in terms of energy. CapEx really comes down to the land cost because the amount of line of sight to air handling units, due to the massive reductions in airside losses, for liquid cooling, particularly if you go down the immersion route, really can decimate the amount of floor space that you need. But there's no one size fits all, of course, as we said earlier on. And I think the unfortunate thing is to really find the truth for a particular site. We're essentially dealing with a hybrid. So it's the same complexities as you get from a brownfield assessment, where you have different cooling types alongside each other. But broadly speaking, there are savings at OPEX and CAPEX to be had.
Hey, Matt, do you want to respond to that?
Yeah, Andy summed it up earlier. It's a business decision. I don't think the OPEX part of it is quite what people would lead you to believe. The whole trade-off of energy efficiency, cost, all the rest of it. However, deployment and adoption generally drives economy of scale. Also, a very good one is sheer necessity. If your chip density is so high that you have to go direct to chip with a particular system, then you're going to have to do it. That's an easy one. Floor space wise, they're all pretty neutral. The need for CDUs, for rear doors, direct to chip, that sort of thing, it's not really making much of a difference, is it? I think one of the insolvable issues at the moment is if you're looking at the horizontal single phase immersion sort of bath type, that's probably not feasible at a hyperscale at the moment. But I could be wrong with stacking and all the rest of it. Floor loadings is the only thing that would concern me with that. But as a value proposition, floor space, yeah, they're all feasible. It's exactly what Andy said. It's a business decision at the end of the day.
Excellent. Okay, so Andy, this question is from the audience, and it's to what extent are PFAS-free fluid choices currently available on the immersed cooling market?
Yeah, it's a really key topic, this one. So PFAS is in particular relevant to two-phase, where you're vaporizing the liquid to affect the heat transfer at the chip level. The regulations mean that the most commonly used liquids for two-phase immersion cooling are not going to be supported going forwards. And we've also seen the announcements from 3M to that effect. Alternatives are available, just like there are for refrigerants in chiller plant. And I believe that these have been looked at very carefully from the two-phase immersion companies.
Okay, and that's a great answer. Thank you. And Matt, with the forthcoming F-gas regulations and the changes to the refrigerants, would you like to respond and kind of give us some view on what refrigerants we'll be using in future?
That's a $66 billion question, isn't it? I think, in my mind at least, it's pretty clear in Europe. It's going to be R32 because it's the only non-PFA that we've got solutions for in terms of compressors and all the rest of it. There's lots of talk about using things like CO2 and things like that, but transcritical cycles, they don't look particularly good at high ambience. Well, we all know that it's pretty much useless. Although then it becomes an environmental thing rather than, am I going to have an environmental gas burning absolutely tons of energy because it's less efficient if I've got green, sustainable power? There's always a trade-off. It's an impossible question, I'm afraid, John, but I would hang my hat at the minute on R32.
Okay, and so not looking at R1, 2, 3, 4, ZE or YF?
Well, ZE and YF are both PFAS, so they're gone, yeah.
That's fair enough. Thank you for that little educational point. And their second question is do we think that the new A workloads will see a rising growth for metro data center markets? And would this lend well to liquid and make better use of the heat? Can data centers actually deliver both social and economic value? Just respond to the first part first, and I'll comment on the second bit in a minute.
Do you want me to take that, Andy?
Yeah, I can start us off, Matt. I'll try. I really believe that's so the edge is a great place to place liquid cooling, because for a number of different reasons, but the impact on the local environment, the density, the energy requirements, just the sheer size of the infrastructure that is needed, really lend it to that. And of course, if for locations where there is an opportunity for heat rejection to be integrated. But to be fair, there's probably, if there's an airside, an air-based heat demand, then that could be integrated more directly. So I think either way you cut it, whatever the cooling solution is, there's opportunities to get creative with the ways that we look at the energy and waste streams. With more close integration, but you've got to get over the sort of planning and regulations and consent barriers initially.
Absolutely. And Matt, do you want to put in?
Yeah, I think, the social and economic value piece is a difficult one to answer briefly, but in terms of the feasibility, I mean, a great one for me, and this has always been my dream, and it's a bit sad, so apologies, but Centre Parks, go over Christmas with the kids, and you've got cabins everywhere, a massive swimming pool, and a gas boiler in every single one in a little cupboard. Take the gas boiler out, put a rack in, distribute it AI workload or whatever, HPC workload, heat the cabins up in the winter, heat the swimming pool up 24/7, boom. Beautiful use case.
What do you do in the summer?
Well, massive dry cooler on the roof.
You grow lobster. Come on.
Yeah, exactly. I mean, I think, and I think this comes back to my earlier point. Liquid data centers to date haven't been that collaborative or very community focused, although there are isolated examples of people that are saying that they are community focused and they are collaborative. And I do think that moving forward, they are going to have to change their view on that. They are going to have to be more integrated and collaborative with the local community. And I think the legislation is pointing in that direction as well. So I'm not quite sure how much time we've got left. I think we've got about 10 minutes. So my last question, my second to last question, is: do we think that the EU legislation will change the way that we design data centers moving forwards, moving away from air to liquid, or are you still going to hang your hat on this hybrid solution moving forward?
I'll chip in. So no would be my answer. Legislation won't affect anything. The reason I say that, liquid cooling isn't necessarily more efficient. I've done that to death just now. And where it is, it's not massively different. If we talk about the temperature stuff again, you're still going to need chillers, even in locales like Ireland, even in some parts, the north of the Nordics still have some peaks. You're going to end up with a need for some sort of, mechanical compression. From an environmental perspective, some of the liquid cooling stuff looks really appealing. Direct to chip looks great. Single phase looks great. Again, the sort of the big sort of oil, liquid plastic type, baths, they don't look so environmentally friendly for me. Andy, I'd love to hear your thoughts on this, because I've been trying to get hold of, and this isn't a dig, but I've been trying to get hold of data sheets for, these fluids, and nobody will give them to me. I've heard them called zero GWP recently and biodegradable, but when I see immersion companies being sponsored by Shell, Exxon, BP, I start to question, where is the environmental part of this, because it's all made from oil.
It's a derivative from a process that makes oil, but it's not made from oil, directly. But there's a okay. So the liquid itself has a life cycle. Its GWP is explicitly known. It's in the public domain for most of the liquids, and the carbon kilograms, meter cube metrics are known. I think some of the fluid vendors do publish this, not all of them, but that information is available. And Matt, if you need help to find it for some, then I can help you with that directly.
Oh, cool.
This is what I love, the collaboration.
Yeah. So, but I think that but for some fluids, the GWP is incredibly high. Hence, why we see regulations. And I think the environmental regulations for data centers are pretty well conceived. I think in the sense that they don't just single out a single metric, not just energy, not just water usage, not just energy recovery. And there's a list. It goes on. There's maybe 5 different metrics. And the smart thing about it is, it's very easy to achieve a single target. But if you have to find and optimize things by balancing, then it leads you forward or down a path in a certain way. And so whilst you can come up with very energy efficient air-based systems, there's a penalty somewhere. And it's the same for any engineering system. If you want something, you've got to give away something else. Hence why the context is so important we're
Very
discussing
true.
these.
So there are actually 8 ISO 30134 metrics, which include power utilization, energy waste heat reuse, renewable energy, water usage. There's a couple for IT energy efficiency and utilization as well. And that's going to be interesting because the new legislation does call for some of those metrics to be reported, and I'm not convinced that a lot of the data center operators in Europe at the moment have actually got the mechanisms to actually start delivering that. So that's going to be very interesting. I think next year is going to be very interesting. So my final question, and this is to Matt, because I know you've been chatting to our very good friend, the man whose head is always on upside down, Mr. John Summers from Rise. And you spoke to him about some thermal issues a couple of weeks ago. Would you just like to cover those for us briefly?
Yeah, I love talking to John. I think that I'm I know a little bit about what I'm talking about, and then speak to John, and it all goes straight out the window. So that was fun. I was randomly talking to a friend of mine, and he said he just bought a new laptop, and it was thermally throttling all the time, and started looking at it, and what the power was, and all the rest of it. And got talking to John, and he was kind of saying that if we take it to data center scale, AI scale. The NVIDIA H100 is the GPU or the AI processing unit that everybody is using now. And that has a heat flux. And John did some back of an envelope calculations that is nearing the heat flux of a nuclear reactor. And that's actually at a scale of an 814 square millimeter die. So on a 814 square millimeters, the heat flux of nearly a nuclear reactor, that's starting to get a little bit mental. Are we going? And I don't know the answer to this. This is my sort of, just verbal diarrhea, if you like. But we're going down a route, in my opinion, where the chips are surpassing thermal limits, irrespective of what heat rejection method that's being used. Will there be a change of architecture, much like when we went through the bipolar to CMOS days? Will it be ARM? Will it be RISC? A really interesting thing that John mentioned and I looked into was that mobile phones, they have huge processing power these days. But they're on a completely, or not completely, but they are a different architecture. It's a system on a chip with segregated responsibilities. And will we see that sort of thing happening? Will there be a complete change? Will the RISC thing come through? Will there be, almost another hybrid solution that goes on there? And I don't know. The scary thing for me was that when John mentioned that the actual TDP of that H100 should be 1440 watts, and it's actually classified as 700 watts, that means that over half of that chip is dark silicon. So it's off at any one time. So to me, I thought of an interesting parallel, which was, well, instead of trying to cram more out of it, are we actually at a point where we can make the chips smaller and smaller at a nanometer scale and have more of them dark, in the sense that we're actually making them more power efficient? So instead of cramming more, flops or whatever you want to measure it on per second, you actually make it more efficient. And is that where we start to reduce to 1 rather than the point X? And I don't know if that's a thing, but it just came to me. I thought, well, maybe that's very similar to, what we've been trying to do for years and years in air cooling and, for any liquid cooling, really. The affinity laws reduce the speed.
And Andy, have you got any views on that?
Yeah, I mean, no doubt there'll be a shift at some point. I think the timescales are unknown, but I think within the next 10 years, we're going to see a shift. We're seeing from different vendors, the chip OEMs, the architecture on the silicon level is already changing, and there's some sort of separation between the vendors as well on what routes they're taking forwards here. But there's no matter what the cooling solution is, anything that they can do at the chip level to distribute the heat, to reduce the spreading thermal resistances before you even get through the material layers to the liquid or to the fluid, should I say, is going to be beneficial. But thermals come last, right? In electronics, it's not always a primary consideration, but maybe some more joined up thinking between the semiconductor and the thermal teams is going to be necessary, and I really look forward to that day.
Yeah, I think you're bang on there. I've reached out to a couple of the OEMs and the equipment manufacturers and asked them, why aren't you talking more to the people that are actually hosting your equipment? in their own facilities and expending huge amounts of energy and waste on this stuff. And it's time that you guys stepped up and definitely looked at the one side of the PUE. Okay, I'm not sure how much time we've got left. So if Kaylee could throw in yet, how much time have we got?
We can go for another 10 minutes if you want to have another.
Unfortunately, I do have to be somewhere else.
No,
so
I wasn't sure if you were feeling out whether you could get another question in there or not.
No, I can get another question. There's not a problem with another question in. Right. Let me see now. Another question. Interesting. Now, this is totally unscripted, guys, so you'll have to bear with me on this one. And I've got to think of this myself. So this is me thinking on my feet and clearly failing at the moment. I'm going to come back to the power question, right? Because I really do think we've got a bit of an issue here. You know, I'm looking through LinkedIn and looking at the trade press, and I'm seeing data centers, 3.2 gigawatt data center just to the south of Dulles Airport. And I was in Virginia a couple of weeks ago, and I drove through part of data center. I think I was telling you about this last week, Matt, in Ireland. And there was about 5 or 6 data centers there that hadn't been energized yet. Right. And there is Dominion Energy do not have the power to fire up the existing facilities. And yet I just can't understand the mindset of some of the operators and companies that are building data centers to want to locate in an area that there's no power. I mean, I just can't understand it. I mean, you know, here's my question. So where do you think the next big data center construction hotspots can or should be?
Should be. I don't really have a view on, John. Will be Saudi, Middle East, APAC. It's all going out there. It's all going out to the east. I think Saudi will be a very, very big boom.
Interesting. And Andy? You're on mute, I think.
Sorry, same, simple. Yeah. I think APAC's where we see a lot of demand. There's been some changes recently in APAC that's sort of opened things up a bit. The requirements regarding power, where the power comes from, if they need water, which they almost certainly will do, for cooling, is they need solutions for that. And there's some challenges there due to the need for desalination and so on. But yeah, just the demand, the rate of business growth in that territory is just means it's a very clear area that's going to be growing very quickly indeed.
And that's very interesting. I like the way that you've linked in desalination there, because obviously data centers can provide desalination elements of the desalination. We were working with a guy that built a desalination stroke data center cooling solution in Malaysia a couple of years back. All right. Well, I've run out of questions. So I think my opinion is the jury's still out. The one thing I would say is I do recall being at a data center networking event a couple of years ago, and somebody quite senior within one of the property companies came up to me and said, "Why hadn't there been a greater take up of liquid cooled solutions?" And my response was, well, look around you. Can you see any of the immersed compute and other liquid solution vendors in attendance? And unfortunately, none were to be seen. So perhaps this is more of an awareness question and a technology solution. And perhaps the liquid immersed compute vendors need to get out and be more social. So, and with that, I'd like to thank my guests, Matt Evans from Flakt and Andy Young from Asperitas. And this is John Booth with the final words of "Let the battle commence."
Yes, sure.
I just want to say thank you again. I know you've got to rush off, John, but thank you so much for moderating the session and keeping it to time. And thank you both to our guests. It's really been great to have you online with us today. And I think we've touched again on a lot of these sort of overarching points that we've come across in all these sessions of working more collaboratively, working within the communities we're in, and changing the perception of data center and how sustainable we can be. So thanks again. And it's been a pleasure having you with us today.
Thank you very much.
Yeah, thanks, Kelly. Thanks, John. Thanks, Andy. See you. Bye.
Thanks, everybody.